Good evening, everybody. Thanks for coming. So hopefully I can see some familiar faces from university, but I can also see some very young faces. So hopefully by end of an hour today, you will learn how great engineering and science is, and you want to pursue and let's try change this planet together. So my talk is, I'm engineer and scientist. I work in electrical engineering and electronics department here at the University of Liverpool. And I would like to walk you through in the next 10 minutes about some exciting stuff that has been happening for the past 50 years. So directly from Silicon Valley, the question is, end of Moore's law, a blessing or a curse? So 2015 is to be in maybe 3-4 weeks down the line. That's it, finished. So it marks an anniversary of 50 years of Moore's law. So, and some of you know it for sure, but if I show you these pictures, hopefully it will work, this thing. Sorry. Yes, if I show you some of these, you recognize your very familiar gadgets. iPads, mobile phones, your fancy camera, laptops. So what you have been noticing it over the years, your nice mobile phone went lighter, you don't need battery as much, your nice camera takes much nicer pictures, whatever. So you have noticed a revolution in electronics driving that all these products are becoming much more sophisticated. So this is very visible to us, but also there are all sorts of things. You sit on the plane, you go through the security checks, you have a surgery, you know, all these implemented different type of the circuits, integrated circuits are integrated in all these, if I can say, our very favorite gadgets. Some of you will get, I'm sure, a new type over Christmas. So what has all this got to do with Moore's law then? So it all started in 1965 when an engineer, he is now a very wealthy man, and he's one of the co-founders of a big company. You probably heard Intel. If you haven't heard about Intel, then you just turn your, if you open your mobile phone, you will see a little square, and it says on the back, Intel. Anyway, so what Gordon Moore, engineer in 1965 noticed, it was just a couple of years after very first MOSFET transistor was invented. What he has noticed is the number of components, the number of transistors on the chip increased, doubled, and also not only that doubled, performance was much better, but even nicer thing is that the cost also dropped. So if you look at this curve here, you can see this minimum, which is called sweet spot. So if you go further, if you want to put more components on a chip, it won't be business because you get more. It will cost more. So there is for each generation, for example, if you compare 1961 and 1970, that sweet spot, is changing. So you put more components on chip, and it's much better performance, and the cost is reduced. How fantastic. And what he said is, okay, I can see this trend, and maybe it will happen just for, this is what he said, over the short period of time. And then in 1975, he said, okay, the transistors will double in 2 years, and later he changed that to 18 months, which means exponential growth. So it's 46% per year. We will have more transistors around chip, they will be more powerful, and they will cost less. Wow, fantastic. So this is the curve. This is what has been happening from, let's say, 1972 till projected 2020. So consistently, the length of the channel of the transistor was becoming smaller and smaller. Here, this is a cross-section of the transistor. And I don't want to bore you too much about that. Transistor is like a switch. So you have, this is silicon, you know, you sit on the beach, all around you is silica, basically oxidized silicon. So it's a very abundant material. It's very cheap. So silicon, and then you have some doped regions of silicon, and then on top of it is another material which is oxide, is dielectric, and then on top of that dielectric you have metal. So how does it work? You put some voltage on the metal, and then that voltage creates some electrons channel, and you have a current flow, so that there will be on state. If you don't have voltage here on the gate, there is no channel, and you have an off state, and it's zero. And all digital circuitry, 99% of digital circuitry is made using this type of transistor, so it acts like a switch. So if you look at the diagram, so as we were cramming more components on chip, what has happened is that the channel length was decreasing, decreasing, decreasing. And we had this trend, 2014, 10 billion transistors and a very, very, very small price. So that's great, but at about 2000, 2003, you probably heard, oh, it's a very big problem because this, on top of silicon, there was a material, the oxide material was SiO2. And SiO2 with silicon works, is like a marriage made in heaven. It works very nicely. I don't have much time to talk about it. But anyway, if you make this thickness of this material, SiO2 on top, very, very thin, there is quantum mechanical tunneling, and you can't switch off, you can't have like switching on and off situation. So to give you a little bit of idea, it's like when you have a faulty faucet, you know, it just drips off. It doesn't, it's on all the time. You can't switch it off. It doesn't produce zeros. So it became apparent that new material is needed to reduce this leakage. And I, with a group here in Liverpool, in Tripoli department, worked for experts in Europe, various groups, on this high-K new type of materials to replace this silicon dioxide. And then, you know, the good news is the scaling has continued. So Intel, 2007, a big company, has introduced a new type of material, hafnium oxide, and we are, in terms of scaling, here. So if you look, this is the latest graph. So what this node means is what is the length of that transistor. So currently we are in, so I have been working on, in this area here, 22 nanometer, 40 nanometer nodes. So we are now 2015. So now the minimum feature inside of your mobile phone, whatever you have, the transistor is 14 nanometer. They said they should have 10 nanometers soon, but if you can see on this graph, it's delayed to first half of 2017. So in order to give you an idea how amazing this is, there are some fun facts regarding 22 nanometer transistor. So initially, when all this started, you could physically put a transistor. Now, inside of this pin, you can put 100 million of them, 100 million. The transistor can switch in 1 second 100 billion times. If you are you to do this switching, it would take you 2,000 years. So the computational power is just amazing. This is a strand of hair, human hair. You can fit 10,000 transistors in just what you see in your hair. Also, the price, but look at this, phenomenal price drops. So the factor of 50,000 drops. So if same thing happened to our car industry, the car will cost 2 pence, guys, believe it or not. Right, so you may ask, well, oh, that's great, but then we just continue on that, you know, it will be fantastic, we just, well, we can't catch this rabbit. And the reason why we can't do it is this bit complicated graph, but it's to do with the way we print these transistors. So you need to have mask, and you have these tiny little features, this is called lithography process. So lithography is transferring your little features on the mask onto semiconductor chip using electromagnetic radiation. And if you are to do such a tiny small transistors, to put more transistor on chip, you need this is called extreme ultraviolet radiation. And that, guys, cost a lot of money. Not that it cost a lot of money, but also it seems at the moment they are trying to develop that for the past 20 years, but it didn't really work as they wanted, because throughput, they want to have to be viable economically, 100 wafers per hour, and currently with this they are achieving 30, so it's not good enough. And as you know, if you work in industry, it's making money, so if you don't make money, that's it, you are dead, you don't proceed with this. So there is currently some ideas to move into 3D integration. I'm not going to bore you with that, it's another principle. However, to give you such an idea, we as a society, as a modern society, you know, what do we depend on? Transportation, food, whatever. None of this in the past 20th century followed this phenomenal exponential growth. Everything, if you look at the lighting, if you look at the transport, if you look at the food production, if you look at nothing is, it can't follow that. It's just few percent. So this is what I heard recently. I was in San Jose, and I was sitting, as you're sitting now, and listening to some experts, industrialists. So this is what they say. 5 nanometer is our final frontier. If we haven't reached it by now, I think it's difficult to say, because if you remember that sweet spot that I was telling you, at the moment is kind of leveling out. So if we go up, it's not economically viable anymore, so Moore's law will not be continuing anymore. So it's fantastic the way we made these microchips. Perhaps is the biggest triumph of engineering so far. So the complexity of it, the processes, everything, and also the phenomenal computational power that will bring us. And that leads me to a very last slide. I hope I haven't gone over my time. Right? So all of this will be pillars of the society that we are building now. So all these driverless cars, Internet of Things, smart homes, moving into renewable energy, we will exploit our mighty chips, microchip. My message is making devices, making things matters, and you need to decide for yourself whether you want to make money by rearranging it or by creating wealth. And my personal mission is the latter. Thank you very much.